Hi. So today we will discuss two other crystal structures, zinc sulfide and cesium chloride crystal structures. So in order to understand these crystal structures, we have to go through these parameters, that is the Bravais lattice upon which these structures are made up of, or then coordinates, then coordination number, unit cell and number of atoms per unit cell, and atomic packing factor. So this zinc sulfide occupies in two different forms, one alpha zinc sulfide and the other is beta zinc sulfide. This alpha zinc sulfide is also known as zinc blende structure or sphalerite structure. This alpha zinc sulfide or a zinc blende structure adopts face-centered cubic Bravais lattice. So it's a cubic variant, and at higher temperature, maybe above 1020 degrees Celsius or more, this alpha zinc sulfide changes to beta zinc sulfide. And this beta zinc sulfide use hexagonal Bravais lattice, and it is called Woodside structure. So we have two structures, one is zinc blende structure, also known as sphalerite structure, another is Woodside structure. So this Woodside structure is known as beta zinc sulfide and the other one is alpha zinc sulfide. So today we will be discussing this zinc blende structure or alpha zinc sulfide, and it is an extension of this face-centered cubic Bravais lattice. In diamond cubic crystal structure we have seen there are two interpenetrating face-centered cubic Bravais lattices, of which one is pushed along the main body diagonal by 1/4, 1/4, 1/4, and two face-centered cubic Bravais lattices are attached with identical atoms, that is carbon atoms or silicon atom or germanium atom, etc. So that gives diamond cubic crystal structure. So here I suggest you to watch lecture 11 and 12 before going through this particular lecture, because that will give a elaborate discussion on diamond cubic crystal structure, and zinc blende structure is an extension of the same pattern, where we have used these two face-centered cubic Bravais lattices and one is pushed. So here also in zinc blende structure we have got two face-centered cubic Bravais lattices or two interpenetrating face-centered cubic Bravais lattices, of which one is pushed along the main body diagonal by 1/4, 1/4, 1/4, and two interpenetrating face-centered cubic Bravais lattices, that is two lattices are attached with two different atoms. One is zinc ion and the other is sulfide ion. That is, in diamond cubic crystal structure there are all the lattice sites are attached with identical atom, but in zinc blende structure these different or two set of lattice sites are attached with two different atoms or two different ions, zinc and sulfide ions. So we have got two face-centered cubic Bravais lattices. So one of the face-centered cubic Bravais lattice is attached with sulfide ion. So the corner positions and the face-centered positions are attached with sulfide ions. So here sulfur face center, here there is sulfur, here sulfur, then back face center there is one sulfur, and front face center also there is sulfur. And the second face-centered cubic Bravais lattice is pushed. So if we carefully analyze what we have seen in our diamond cubic crystal structure discussion, that is there are 4 atoms of the second face-centered cubic Bravais lattice will also come inside this first cubic Bravais lattice. So here if we analyze the sulfur ions or sulfide ions, the lattice positions are 0, 0, 0, then half, half, 0, half, 0, half, and 0, half, half. So this represents the coordinates of the sulfide ions in the first face-centered cubic Bravais lattice, whereas in the second face-centered cubic Bravais lattice, which is pushed along the main body diagonal by 1/4, 1/4, 1/4, therefore zinc ions will have coordinates at 1/4, 1/4, 1/4. So we are speaking with respect to this particular face-centered cubic Bravais lattice. So the position of zinc ions are 1/4, 1/4, 1/4, then 3/4, 3/4, 1/4. So we are just comparing same pattern. Then this will be 3/4, 1/4, 3/4, and third one will be 1/4, 3/4, 3/4. So these are the coordinates of zinc ion, zinc 2 plus, and these are the coordinates of sulfide ions. Or we can say that sulfide ions, the lattice positions can be represented as 0, 0, 0 plus phase centering translation, and the zinc ion 1/4, 1/4, 1/4 plus phase centering translation. So that is how we get the coordinates of sulfide ions or sulfide and zinc ions in zinc blende crystal structure. So when we go to the unit cell of zinc blende structure, it is a face-centered cube. So 8 corner positions and 6 face-centered positions of this cube are occupied by sulfide ions. So that the number of sulfide ions is number of sulfide ions is equal to 8 into 8 corner positions. So 8 into 1/8 contribution plus 6 face-centered positions, so that 6 into only 1/2 contribution. So that there will be 1 plus 3, that is 4 sulfide ions will be attached or will be part of this one particular face-centered cubic Bravais lattice. And there are 4 more coming in. In diamond cubic crystal structure, we have seen there are 4 atoms of the second face-centered cubic Bravais lattice will be coming within the first face-centered cubic Bravais lattice, and their locations are on the body diagonal. So if we carefully analyze, because the second face-centered cubic Bravais lattice was pushed by 1/4, 1/4, 1/4, so we are getting 4 more atoms within this. Those 4 atoms are part of second face-centered cubic Bravais lattice, and their positions will be on the 4 main body diagonals. So if I mark here, say this is, I mark A, B, C and D. So here E, F, G, H. So there are 4 body diagonals. First body diagonal will be from A to G. So this A to G, there will be a body diagonal. Then another body diagonal is from B to H. B to H, there will be a body diagonal. Then 2 more body diagonals, that is, one is from C to D, that is bottom front corner point to the top back corner point. So this is another body diagonal and this is another body diagonal. And from this bottom face, these 4 body diagonals, if we carefully analyze, we can see that the position of zinc atoms of the second Bravais lattice will be at, cyclically if we move from this corner point, then A, B, C, D, we can see one at 1/4 position, one will be at 3/4 position, then 1/4, 3/4. That is, suppose I am marking this, if I mark 1/4 here, then this will be one zinc atom or zinc ion, then B it will be at 3/4. So this is around half. So somewhere here you will be getting one zinc ion. Then C, it is 1/4 position. So somewhere here you will have a zinc ion, and D again 3/4. So this is around half. So 3/4 is somewhere here. So there will be 4 zinc ions will be coming well within the unit cell. So that number of zinc ions is equal to 4. So total, so number of zinc ions is 4, therefore total 4 plus 4, 8. 8 ions, or we can say there are 4 zinc sulfide per unit cell. So this is how zinc sulfide is formed. So zinc sulfide is formed on 2 interpenetrating face-centered cubic Bravais lattices, of which one face-centered cube is pushed along the main body diagonal by 1/4, 1/4, 1/4, and one of the face-centered cubic Bravais lattice is attached with zinc ions, and the other face-centered cube is attached with sulfide ion. So here the first face-centered cube is considered attached with sulfide ion, and the second one is attached with zinc ion. So we have number of sulfide ion is 8 into 1 by 8 plus 6 into half, that is we are getting 4, and number of zinc ions perfectly well within 4 more atoms which are coming from, which are part of second Bravais lattice. So that we have got 4 zinc ions. So that 4 zinc ion plus 4 sulfide ion. So we have got 4 zinc sulfide per unit cell. And the coordinates of sulfide ions are 0, 0, 0, half, half, 0, half, 0, half, 0, half, half. So it is on this blue face-centered system, and the zinc will be on the next one, that is the one which is pushed, and that will be having, the first one will be, because that face-centered cube's origin will be at 1/4 position with respect to this origin. So at 1/4, 1/4, 1/4 position you will have one zinc, and the others will be at the face-centered position, that is 3/4, 3/4, 1/4, like that you will be getting the coordinates of zinc ions in the second face-centered cubic Bravais lattice with respect to the origin of the first face-centered cubic Bravais lattice. So that is how we are getting unit cell and coordinates. So in this case, each zinc ion is surrounded by 4 sulfide ion, or each sulfide ion is having directly coordinated with 4 zinc ions. So the coordination number is equal to 4. So we have all the major points are there on the board. Zinc blend, sphalerite structure is another term used. Then coordination number is 4, 4 zinc sulfide, zinc blend units per unit cell, and it goes like this. Now we want to find atomic packing factor or packing efficiency of zinc blend. Why do we call it zinc blend? Why can't we call it diamond cubic crystal structure? Because in diamond cubic crystal structure, the packing efficiency was found to be 34%, and only identical atom, single type of atom are there in all the lattice site. But here 2 different atoms are having different radius ratio. This radius ratio decides whether it is diamond cubic crystal structure or zinc blend crystal structure, though both of them are using identical basic structure, that is 2 interpenetrating face-centered cubic Bravais lattice. So the radius of zinc ion is 0.74 angstrom, radius of sulfide ion is 1.74 angstrom, and this ratio is very small, and this ratio tells that this should be in zinc blend, a different type of crystal structure with different packing efficiency. Whereas in diamond cubic crystal structure, this radius of both the radius are same. That is not ionic radius, but the 2 face-centered cubic Bravais lattices are having identical atoms attached, and we have got a different type of crystal structure, that is diamond cubic crystal structure. So now we have to calculate packing efficiency or atomic packing factor. So atomic packing factor is equal to what percentage of the cube unit cell is occupied by the solid material atoms or ions. So in this case, it is atomic packing factor is equal to volume of atoms or ions inside the cube or the occupied by the ions divided by volume of the unit cell, that is A cube. So in this case, if I take this body diagonal, say AG, at the point A there is a blue ion, that is sulfide ion, and at G also there is a sulfide ion, and at 1/4, this is at 1/4. So at 1/4 distance away, that is, this is halfway, and somewhere here is 1/4. So at 1/4 position there is a zinc ion. So here is a zinc ion. Zinc ion is comparatively smaller in size, the other one is bigger in size. So this is radius of zinc ion, and the other one is radius of sulfur ion. So if I mark this point as say O, then this is body diagonal, this side is A. Therefore, face diagonal is, if one side of the cube is A, face diagonal will be root 2A and body diagonal will be root 3A. Therefore, this total distance is root 3A. Total distance is root 3A, and this AO is, if I take AO is equal to radius of sulfide ion plus radius of zinc ion. AO is equal to radius of sulfide ion plus radius of zinc ion. But AO is 1/4 of AG, and there are 4 zinc sulfide per unit cell. 4 zinc sulfide per unit cell. Therefore, we can use this data to calculate atomic packing factor or packing efficiency. So this is equal to 4 volume of 4 zinc sulfide, that is 4 into 4/3 pi radius of sulfide ions cube plus 4 zinc 4 sulfide. So 4 into 4/3 pi radius of zinc cube divided by A cube. What is A? AO is equal to AG by 4. But AG is equal to root 3A. Therefore, this is equal to root 3A by 4. Root 3A by 4. That is root 3A by 4. Root 3A by 4 is equal to radius of sulfur plus radius of zinc. Therefore, A is equal to 4 into radius of sulfur plus radius of zinc divided by root 3. Therefore, A cube is equal to 4 by root 3 the whole cube into RS 2 minus plus radius of zinc 2 plus. So this can be solved, that is 4 into 4 by 3 pi into Rs cube, radius of sulfur 2 minus cube plus radius of zinc 2 plus cube divided by 4 by root 3, that is 4 into 4 into 4 by root 3. I take numerator, root 3 into root 3 into root 3, and this 3 I take denominator, into Rs radius of sulfur plus radius of zinc to cube. Here also there is a cube, because a cube, so one cube is missing here, here also cube. So that's how it is coming, and here you can substitute the values of this radius of zinc and sulfur. Here this 2 4's cancel and this 1 3 cancel with these 2 root 3's. So rest you have to substitute, that is root 3 pi into, this is 1.74 into 10 to the power minus 10 cube plus 0.74 into 10 to the power minus 10 cube divided by 4 into 1.7 into 74 into 10 to the power minus 10 plus 0.74 into 10 to the power minus 10 cube, of which this 10 to the power minus 10 cube can be taken out, then into 10 to the power minus 10 cube, and this 10 to the power minus 10 cube can be cancelled with inner one. So rest, if you calculate, you will be getting the answer 0.497. That is, packing efficiency is 49.7%, approximately 50%. That is, 50% of the available cube space is occupied by solid zinc and sulfur atoms, whereas around 50% is vacant. Whereas in the case of real face-centered cubic crystal structure, the packing efficiency was 74%, and in diamond cubic crystal structure, packing efficiency was 34%, whereas in zinc blende crystal structure, packing efficiency is 50%. That is why it is another totally different crystal structure, that is zinc blende or sphalerite crystal structure. And we have one more crystal structure to be discussed, that is cesium chloride crystal structure. So in cesium chloride crystal structure, the radius of cesium is radius of cesium plus by radius of Cl minus, that is cation anion radius ratio is 1.74 angstrom divided by 1.85 angstrom. So radius of cesium and chlorine, it is nearly equal. So it shows a totally different type of crystal structure. So in many of the textbooks, this cesium chloride crystal structure is presented as BCC crystal structure, body centered cubic crystal structure. But strictly, the cesium chloride crystal structure is not body centered cubic crystal structure, because in body centered cubic crystal structure, all the lattice sites are occupied by identical atom. Its monoatomic system is generally crystallized in BCC crystal structure. We have seen in the case of sodium, tungsten, etc., where BCC crystal structure is seen, but in cesium chloride it is not BCC crystal structure, it is a different crystal structure called cesium chloride crystal structure. Again, like zinc sulfide, cesium chloride also exists in two forms. One is alpha cesium chloride and other is beta cesium chloride. This alpha cesium chloride changes to beta cesium chloride at a temperature of above 445 degrees Celsius, and this alpha cesium chloride is one which we are discussing, that is cesium chloride crystal structure, and the beta cesium chloride is actually exhibiting sodium chloride or rock salt crystal structure. So today we discuss the crystal structure exhibited by alpha cesium chloride, which is known as cesium chloride crystal structure, which is this cesium chloride, basically it is an AX type system where A atom exists, or A atom sits in the interstitial site of 8 X atoms. That is how cesium chloride, it is an ionic crystal, and even non-ionic systems also exhibit this cesium chloride crystal structure. So basically cesium chloride crystal structure is using simple cubic Bravais lattice. It is not body-centered cubic crystal structure, it is not body-centered cubic Bravais lattice, but it is simple cubic or primitive Bravais lattice is used, and there are two interpenetrating simple cubic Bravais lattice. Simple cubic Bravais lattices. Two interpenetrating simple cubic Bravais lattice, of which one is pushed along the main body diagonal by half, half, half. So we have got two simple cubic Bravais lattices. So in simple cubic Bravais lattice, all the corner positions are occupied by atoms or ions. So in this case, chloride ions occupy these corner positions of the first simple cube, and there is second simple cube which is pushed along the main body diagonal. So along this main body diagonal, second one is pushed, so that we have another cube starting from the center point, body center position of this. So that somewhere here you have got another cube. So something of this kind. So this point is, this is your body center position of the first cube, where there is an atom or an ion of the second simple cube is also coming. So that there is, when we are analyzing the unit cell, there is one atom at the body center, and hence in many of the books it is given that it is a body centered system, but it is not body centered crystal structure, but it is a totally different crystal structure where two dissimilar atoms are attached to two simple cubic Bravais lattices, and we call this crystal structure as cesium chloride crystal structure. So here the coordinates of chloride ions are, these are all chlorine, the coordinates of chloride ions, and we can work out this is coordinate of cesium ion. So coordinates of chloride ions are, chloride ion is 0, 0, 0, and coordinates of cesium ion is at half, half, half. So in simple cubic Bravais lattice there are 8 corner positions are occupied by solid atom, so that you will have 8 into 1 by 8, that is equal to 1 atom per unit cell in simple cube. But here there will be one chloride ion and one cesium ion of the second simple cubic Bravais lattice, which is already there inside. Therefore that also comes inside, so that for simple cube this is a case, one atom per unit cell. But in the case of cesium chloride crystal structure, the unit cell consists of, unit cell is again a simple cubic unit cell which is having contribution of 8 or 1/8 contribution of 8 corners plus 1 body center position which is the atom from the second simple cubic Bravais lattice. So, altogether we have got 2 atoms per unit cell, of which one is 1 cesium atom plus 1 chlorine, or 1 cesium ion plus 1 chloride ion combined, that is the unit cell. So, here again we can calculate the packing efficiency and atomic packing factor. So, while calculating atomic packing factor here for cube, so side length is A, and along the body diagonal, this is our body diagonal, and corner position we have got chloride ions, and body center position there is 1 cesium ion which is part of the second that simple cubic Bravais lattice. So, that is coming here, and nearly the radius is nearly equal. So, so these 3 are in contact. So, if I mark this point, say A, B, C, D, E, F, G, H. So, here if we take this body diagonal AG, it is marked in red color. So, this is AG. Along AG at the end point we have got 1 chloride ion, then we have 1 cesium ion, and we have 1 chloride ion. So, this point is A and this point is G. So, we have root 3A is equal to, root 3A is the body diagonal, A is the cube edge. Root 3A is equal to radius of chloride plus radius of cesium, then again radius of cesium plus radius of chloride. So, radius of chloride plus radius of cesium into 2. Therefore, A is equal to 2 by root 3 radius of chloride plus radius of cesium. Therefore, you can calculate packing efficiency. So, packing efficiency APF is equal to, there are 2 atoms per unit cell, 1 cesium ion plus 1 chloride ion per unit cell. Therefore, the volume of cesium plus volume of chlorine all divided by total volume of the cube, that is 4 by 3 pi radius of cesium cube plus 4 by 3 pi radius of Cl cube divided by A cube, that is A cube is 2 by root 3 the whole cube into radius of Cl plus radius of cesium whole cube, where you can put data here, this one, all these you can substitute from here. So, when you substitute and solve, this will be, since the radius of both the ions are nearly equal, approximately this will be again coming 68% or so. So, this is a homework I give you. So you can just try by substituting the correct value and get the exact data. Approximately it will be something of that kind. That is one reason why people consider this as a body-centered cubic system or cubic structure. But in body-centered cubic structure, the packing efficiency is around 68%. But though its value is coming nearly that 68%, but this is not body-centered crystal structure. It's a different type of crystal structure. We take it as consider as a different type of crystal structure, cesium chloride crystal structure, because there are two different types of ions, cesium and chlorine, are attached to two interpenetrating simple cubic Bravais lattices, of which one is pushed along the main body diagonal by half, half, half. Its appearance will be somewhat like a body-centered system, but this is not a body-centered cubic crystal structure. So, will be these two cases we have come across two atom bases, because in the zinc sulfide as well as in cesium chloride crystal structure, that inner position, for example, in this case the body center position, which is not an acceptable lattice position for simple cubic system. So, that particular point, that is, we have got two positions, one is 0, 0, 0 and one is half, 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 they are combined together and that form one basis. So, it is a two atom basis. So, in diamond also we have seen it is a two atom basis. Therefore, zinc sulfide also it is a two atom basis, that is, those 4 atoms of the zinc ions which were inside that face-centered cubic Bravais lattices are to be attached to the latticite, because the inner positions are not acceptable latticite, which we have seen in other discussions as well. So, both cesium chloride and zinc sulfide, they are crystal systems using two atom bases. And in the following lecture, we will be briefly discussing some of the crystal structures which have more than 2 atoms as the basis, or motif consists of more than 2 atoms, and also we will see crystal planes and more in the following lecture. Thank you.